Okay, so the first difference we said was difference between a lesson logic and a lesson plan. First thing Kendall said was, tell me again. I lost track. Okay. All right. So a lesson plan would have more detail in terms of how it's going to play out, what the teacher is going to do, and how the student and anticipated response of the students. Lesson logic doesn't have that. And then you were next, I thought, right? You said no time frame on a lesson logic, where a lesson plan might shoot for certain blocks of time for different activities. Jose, then you said. Okay, all right, exactly. Lesson logic focuses on what they're going to learn, and instead of a lesson plan, is more about what's going to happen, what they're going to do. Another difference. Yeah, Ken? Okay, so this is the big one, right? So this is the big one. A lesson logic. What's the logic of what you're choosing to do? Why? So it outlines the things you want them to understand and why that's important. Why you want them to understand that. So that's a big. Okay. Anything else? So that will be a major component of what you turn in. You're going to be having a lesson logic for for your component, your module that you're teaching. And so that, how long was the video? 45 minutes? An hour? What was it? Almost an hour. Okay, so you can kind of see how long my lesson logic was for an hour worth of class. So now if you're doing a 3-day unit, you see that it's kind of just as a gauge of how long your lesson logic needs to be. Your lesson logic shouldn't be half as long as mine, right? It shouldn't be about the same as mine. It's going to be longer, right? Because you're teaching a lot more than an hour. Okay, if you're teaching 3 days, what's that? At least somewhere between 2.5 and maybe around 2.5 hours of class. If you're saying that classes are 15 minutes or 45 minutes like that. Okay, so make note of that. Make note of that. Okay. Um, so let's look at. I've posted the project requirements and rubric. Oh, you don't see that. So in the course project area, the rubric requirements are now posted, and let's take a look at them. So the 1,400 points, I think I said, don't worry about. So that's what it turns out, and it turns out to be, I think I said 30% of your grade on the syllabus, the 30%. Okay, so the course project is meant for you to do a high-quality implementation of what you have learned in this course. It will address simultaneous relationships among learning, teaching materials, and creative uses of technology. Okay, so this is kind of an intro, just an overview of the project, the mathematics you want your students to learn, the materials, the teaching, how you will handle the issue of equitable access among your students to computing resources. And then it starts what you will submit. Okay, so that's kind of an overview of the components of it. And then what you will submit begins here. So your proposal, that's what you're working on now. Okay, you're revising it, and that's due. The revised proposal is due Thursday, and we really want to outline exactly how you want your students to understand the things that you'll be teaching in that proposal. Okay, and so then this starts the components of what you'll submit for your for assessment. And the first one is mathematics behind what you intend to teach. Okay, so this is strictly you're talking about the mathematics. Okay, if you teach conic sections, what are the foundations of conic sections? Their definitions, important formulas, equations, their derivation. So this is really diving into the mathematics behind what you're teaching. And then in the lesson logic, so what you'll see in this, the way this is broken down, so you're going to create a lesson logic, very similar to the one that you analyzed and reflected on. When you do that, you'll see that some of these things will naturally be in that lesson logic, this A through E. But then whatever's not, you want to then include, and that will fall under the grade of the lesson logic. Does that make sense? So you can read it through carefully. I'm not going to read through the whole thing, but read it through carefully. Compare it to the lesson logic that you analyzed for the assignment. And so you're going to build a lesson logic, and then whatever's in this list that isn't explicitly covered by you creating a lesson logic, then you're going to do kind of in addition to it and put it in that section of your materials. Does it make sense? So for instance, no, this is due at the end of the semester. No, this is due at the end of the semester. This is your project. This is it. Okay. All right. So ideas and meanings you want your students to learn, the ways of thinking you want them to have. Okay. So this is what similar to what you're working on in your proposal. Okay. Meanings and ways of thinking the student must have to benefit from your unit. So these are like prerequisite meanings, okay? So B is like what they need to know and understand coming into starting your unit. And then this is what they're going to attain after going through your unit. Does that make sense? Okay. Didactic objects, certainly those should come into when you're writing out the lesson logic. Actions you will perform and reasons, right? That's exactly the lesson logic, right? Okay, so that's a big chunk. That's what some 35-40% of the project. And then other materials, you're going to have classroom activities and worksheets, homework sheets. Okay, these need to be original. You need to be creating these yourself. Okay, in past I've come across homework that was just completely plagiarized. Okay, and that's plagiarism. So you are creating these. These are your original materials that you're creating to support the activities and conversations that you have in the class. Okay, you're going to do a comparison with a text. So somewhere in the world, you're going to find a textbook that's teaching the same thing that you're teaching in your unit, and do a comparison of the content. If you need help finding a text, I can help you. So if that's something that you don't have easy access to, you can't find one, then I can help you. Okay. Formative assessment. Formative assessment is questions that you're asking as you're teaching, right? So at strategic moments during your lesson, you want to reveal potential or revealing unproductive meanings and ways of thinking students have in relation to what you intend to learn. You're also seeing if they're, you're testing to see if they're understanding on the fly as they're learning. And then summative would be more like a formal assessment, like a quiz or a test. Okay, summative assessment. You want to detail your unit's alignment with the Common Core standards. And then the last thing is the presentation. And so after, we'll have to plan it out. Let's see, how many groups do we have? 10 or 11 groups. So we'll plan out when these presentations will be. Some will be in the last day or two of class, the last week, and then some will be during the scheduled final exam time. Does anyone know off the top of their head when that is? According to so we're going to go right according to the university schedule for Tuesday, Thursday classes at 1:30. Genevieve has it.
Maybe not. The week of finals is the 4th to the 10th.
4th to the 10th.
Yeah, the finals are. Wait, but I don't know when. I tried looking it up to put it in my calendar and I didn't find one. Well, I was looking on your rubric though.
Let's just find it right now. Let's settle it here. Here we go. Yeah, one moment. Okay, Tuesday, Thursday. There it is. Thursday, December 8th at 12:10. So we will finish up the presentations during the final exam time. We won't have time to do all of them during that, but something like half of them. And then we'll pick as we get closer to the end of the semester. We'll decide who's going to go when. Some of you want to get it over with. Others will want more time to work on it, and so you'll go during the final exam period. So your presentation is something like around 10 minutes. You're not teaching your units. You're doing just an overview of what you decided to do in building your unit, your module. Okay, so you're not teaching it with us as guinea pigs as your students. We would not have time for that. So it's just an overview of what you decided to do. You want to make a slideshow presentation for that. Definitely, you want to show us your didactic objects for sure. Make that a part of your presentation. Show us what you came up with, how you intend to use them, the conversation you want to have with those. Okay, and then you'll get points, also a few points, some of the points for the questions that you're asked. So we're all on the same team here, and you're going to help out the other groups by asking sincere and thoughtful questions. Okay, so Ben, did that answer your question? Okay. So so you know now where we're headed with this. This is how you're going to get points.
Is the questions us asking our classmates questions, or what we as classmates ask the people about it?
It's your other classmates who just watched your presentation asking about your unit. Yes. It's never happened. Okay. So you're all doing this as a group. So the lesson logic reflection was individual. That's the last thing. So you all understand what lesson logic is. But yes, now from here on out, when you're building your submission, you're working as a group, and make sure like I said before, make sure you're carrying your own. Everyone's carrying their own weight. You're delegating things to make the workload even, and everyone's carrying their own weight. And if something happens that's not like that, you're going to give me the chance to tell me that. Individually, you'll all fill out a half sheet of paper explaining how it went in that regard, and that will be private. You can privately reflect to me how you thought the group dynamic went and people's taking responsibility. Other questions? Yes, please.
Are you going to attend a class to work on this?
Yeah, so as the days go on, well, you will get some time in class because that's very convenient because you're all together as a group. Any other questions? Yes, please.
How many more GCs have you have other than the ones you went to?
One more. Yep. So there's the falling marbles and one more, and then but the rest of your work is working on this project. Yeah. Yeah. So these are the most important ones. They're weighted heavier as the sand unloading was. Yeah. All good questions. Okay, and one more thing that I posted. In terms of submitting the project, when that gets close, when we're a week away or so, then I'll explain to you how you're going to submit all these materials. So don't worry about that for now. And then that will be due before your presentation, right? So you have to have that turned in by the time you give your presentation. Okay, I posted another thing in the 250 course project, and this is a lesson building general outline. This is just a bullet it's kind of a way to think about how would you develop lessons. So first thing, and this is part of your proposal, right? In order to teach for meaning and understanding, you must have the understanding yourself. And that's why I'm really focusing on you guys coming up with the details of what you want your students to understand as the result of your unit in the proposal. Okay? So then, so you understand the mathematics, and then you're pinpointing the specific and precise ideas, concept meanings, ways of thinking you want your students to come away with. And once you do that, once you pinpointed those very specific ways you want your students to think and understand, then you need to imagine the conversations and how they would progress to develop the students' understanding. So what would it take to get students from point A to bullet point B, right? What would it take to get your students from they've never seen this before or they have a vague idea to these types of understanding and way of thinking that you've already outlined in bullet point B. Okay? And so then you design visuals to support those conversations. So oftentimes I see students and they're like they put the cart before the horse because it's like, ooh, I could create this kind of cool thing with GC, and then they're thinking about the conversation or what they want the students to learn. Right? It's the other way around. The visuals that you create and that you imagine come out of this conversation or this development phase that you've envisioned for your students. It's like, okay, so how could I support that progression of my students, that journey my students are going to take? How can I support that with a visual, with a didactic object? Okay, and then the last thing is then create a specific action plan for the progression of the lessons. So as you're just in a just kind of overall recommendation of what it looks like to build a teaching unit of 3 days. So that's there for your reference. Does that make sense? Any questions on that? So that's right here, lesson building general outline. Okay, so yeah, so the important thing is that you don't just jump in. You're not thinking about what cool thing could I make with GC, and then think, all right, now what am I going to teach with this? Right? That's totally backwards. Right? That's totally backwards. It's what are the understandings I want my students to have? How am I going to get them there? What's that journey look like? Okay, and now what are the visuals and conversations and objects that will aid in that journey? Okay. So you have Thursday, then you have most of the groups have the revised proposal to do, and then you're once if that revised proposal is approved, if I give you the go ahead, then you're ready to just go to work. You know you have all the outline of what you need to do. Are we good? Okay, so let's talk about falling marbles. Is it big enough? Can you read it? Okay. So here, let's just do a full demonstration of this. I don't know, I didn't really watch the video closely. I don't know how much detail it went into. But here's what it looks like. So fictitious marble gets a running start. So if I come down here, geez, sorry. Let's try that again. I need to make it smaller. Okay, there we go. That's the best I can do. Okay, so watch. So when you hit play, fictitious marble gets a running start, and then when it crosses the line of the height, that's when the real marble starts to drop. Okay, and the fictitious marble falls at a constant speed. The real marble falls as a marble would fall in the real world. It falls by gravity. It starts at the exact moment the fictitious marble passes it. So the point of this is give the fictitious marble a a constant speed so that they land at the same time, or they tie, right? So that they tie. So right now, as soon as the fictitious marble hits, this is the clock, it stops. Okay? It tells us that it took 8.15 seconds to drop. And then when the real marble hits, we see that it took 10.07 seconds. So those are just variables, right? This is just a variable that I've defined in the rest of my code. And then I'm just showing the current value of the variable. So the variable is designed so that it's the time that the fictitious marble has been falling. And when it hits the ground or hits the x-axis, it gives us that final time, likewise with the real marble. Okay, so my FM time, my real marble time, those are just variables I've defined in such a way as that they're showing the time passed since it started to fall. And notice those both start, the fictitious marble, they both start when it passes the real marble. So ready? 0, start together. So the amount of time is the same as they're falling. And then when the fictitious marble hits, its time stops. When the real marble hits, its time stops. So then let's play the game. So figure out what is in this scenario here. So, and so then the height is adjustable by a slider. Right now I have the height at 1,630 feet. That's this line right here. That's that gray line right there. So let's show you that later. So let's do this much. So right now we're starting at 1,630 feet. The fictitious marble has a 500-foot head start. No, that's right. 200? Yeah, 200-foot head start. So let's play the game so you guys figure out what speed should I choose for the fictitious marble so that they tie, so that they hit at the same time. Go. Yes, ma'am. You want to do it? Okay. All right, Shanley, tell us. What do you guys think?
I got 161.867.
Okay. Really, just an answer?
Oh, well. I mean, basically, you do that by dividing the initial height by the time that it took, so then you get meters per second, like how fast it's traveling.
Okay.
The average speed that the real marble falls.
Okay. So you're trying to calculate the average speed that the real marble is falling at.
Yeah, because then that's the average speed that the fictitious marble will be falling.
Because what is average speed? It's a constant speed. Which constant speed is it? to cover the same amount of distance in the same amount of time. So I think this is what you said, right? 1630. Okay, so we can enter that in as that. And so let's see what happens. Oops. Okay, let's see how we do. How to do, yeah.
Why does the fictitious marble start higher up?
Cool.
I'm good with that.
Yes, just do you want to reproduce this exactly? Okay, so when in doubt, make it look like this. So yes, there may be details where that's not important, but if you're not sure, then just make it look like this, and then you're in the clear, right? Yeah. But there are things that if there are certain things that if it's different, that's not good. So just to be safe, make it just like this.
Is this another one of those situations where there's a function that controls the rate of the one marble, and when we change the function, it has to work for any function? Or is this
For the real marble?
Yeah.
No, because you want it to fall like a real marble would fall, and there's only one function for that, or one formula for that. So yeah, so we're not going to change that. Yeah.
The labels, did you use a point and type in label, or did you use
For what now?
for like fictitious
I
marble?
dragged and dropped all of this text. So I did this text in text lines, and I dragged and dropped all of it. But if you're on PC, you're gonna do symbols. You do not have to do this on PC. Yeah, so make labels to write this. Yeah, make so you know which marble is which. Yeah, on a PC for sure, you want to use labels to have this text showing exactly which marble is which. Okay, for sure. But on PC, you don't need to do all that with labels or with symbols. That's overkill. What's that? Yeah, if you can't, if it's not working. Try to make it work with the full words, but if you can't. Okay. So question. So this is now when real only is at 0. Okay. So this is when real only is at 0. Any questions on this? There's the slider real only. So meaning it's not real only. It's both marbles. It's not just the real marble. So when real only, so I'll show that in a second. So questions about this. So the fictitious marble has to fall at the speed. So whatever the user puts in, it's got to fall at that speed correctly, and it needs to, when it hits the x-axis, needs to stop at the x-axis and report that final time. Same thing with the real marble. Okay, and that needs to work for any height from 1,000 to 2,000 that you can adjust with this slider. So now I made it lower, and it needs, when it hits the x-axis, it needs to stop. What's fix what? There's nothing to fix. I just showed you a different height. You want to do it? What would it be? Wait, what do you mean? Generalize what?
On RGC,
right.
You want us to be able to do it so that if you change the height, that it automatically
That it does what?
It makes the ones fall. Like it makes
No.
the real ones. No, you don't.
I want it to work just like this. That if I put in, I want to come up here and put in 100, and now I have a new initial height. It needs to fall correctly. It needs to fall according to the height and the. So now I put in 100 for this new height, 1165. And if you were to do that on yours, this is what it should do. Does that make sense? So the game is after the program is done, you play the game with your class. You pick a height, and they have to figure out the speed. So when you're before they figured it out, you're just going to put any old speed in, and it has to work according to that speed. Is that better? Does that make sense? You're creating the game. You're creating this file that I'm showing you right now. You're creating this file exactly. So I can come up here, and I can make fictitious marble speed 1,000, and this maybe this will be cool here. Oh, it didn't like that. Let's see. And that's what yours should do. So I just made the fictitious marble speed 1,000, and it should do that. Initial height of 1,000, sure. And okay, so there's a speed of 2,000, and so that would take 0.5 seconds versus 7.885 seconds. Okay, so then there is real only set to 1. And so what this does is the fictitious marble never falls. And as soon as you start the end slider, the real marble starts at time 0 and starts to fall. So now I'm going to hit the end slider. The fictitious marble it's not going to move. And as soon as you start, the real marble times clock starts and it starts to fall. And same thing, it's going to hit at 7.885 and then stop and record that time. So there's no head start, and it just falls. Does that make sense? So this is now when real only is set to 1. As soon as you start the end slider, that starts the real marble falling and starts the real marble time clock. And like before, it'll stop when the real marble hits. So what happens with n is different. So the way that n works is different. Because if I turn real only off, what does starting n do? Starting n starts the head start. It depends on the speed. Right? Depends on whatever the fictitious marble speed is to fall that 200 feet. So it's after it falls that 200 feet and crosses the height of the real marble, it's when the real marble starts falling, and the time clocks, both time clocks start when it passes. So that real only is a different scenario as in terms of the times. Okay. So I think I've covered all the aspects of it. Anyone have a question? Okay, so the past semesters have shown that this is a challenge, but it's an attainable challenge. You can do it. You just have to work at it. And you're not going to sit down and do it in one sitting, right? You've got to work at it, think about it. Some of you have already started, that's good. And then come back to it many times. What's that? No, because real marble speed is acceleration according to gravity. So I've given you if you go to the assignment post, I gave you. So this is all in feet. It's in feet and seconds. Here it is. So here's a little info. So you'll have today's video that I just went over, and there's another. This is another video. Don't remember how helpful that was, but this video in class that you're watching right now should be enough. So the distance covered by an accelerating object is 0.5 at squared. Acceleration of gravity, you want to use 32.17. Okay, feet per second per second. That's the acceleration of a falling object in feet units. Okay, so this is just overview. The y-axis, initial height, they're in units of feet. The end slider value represents the seconds since the fictitious marble began falling when both marbles fall. That's what the end slider is. Or the seconds since the real marble began falling when only the real marble is falling. So remember, when they're both falling, the fictitious marble gets that head start, and as soon as it starts to move, it's your end slider.
So the end slider is more like the run time, and the two values of real marble and I guess fake marble, that is only based off of time past the line at the start.
Time falling from the initial height. Yep. So yeah, the real marble time and the fictitious marble time, those variables are time since leaving the initial height. Yeah, and the end slider is like time since you started the animation. Yeah. Other questions? Okay, so you have 1 week, and so work on it, think about it, put it down for a while, get help, work on it some more. Don't try to do it. Start it Sunday night. Don't try to start it Sunday night and have 2 days to work on it. It's not gonna fly. Okay. Get help. Okay, so if you can't make my Thursday office hours, then you can make an appointment. I can be available Monday or Tuesday morning. Okay. Friday we don't have class, so I'm doing school. Questions about falling marbles? Okay, so we had started talking about the reverse process. I think that was a week ago or something. So we're going to review what we did. So if you have your old handout, put it back. Don't take it out. We're going to kind of put it away. We're going to, just as a review, we're going to kind of redo part of it. So we're going to redo part of it just to get warmed back up again. Okay, so we're talking about the function for the volume of a sphere with respect to the radius. Okay, and so this is that accumulation function, accumulation of volume of sphere. That's really fast. Let's slow that down a bit. Oh, and in terms of like, someone asked about this. This is a good question. In terms of just like visually how fast the animation is going, so you can just adjust the number of steps in your end slider. If you want it to slow down, you're gonna just include more steps. So if you wanted to kind of simulate seconds, like be close to simulating seconds as they go by, just mess around with the number of steps till it's close. So this is going too fast, so I'm going to just crank this up to say like 350. And so then that now it appears to go up a lot slower. So that's how you can just change the appearance of the speed of the animation by changing the number of steps on your end slider. Okay, so we've got intervals of 0.4. And you're starting by what? You're going to sketch the approximate accumulation function. Is that the first thing it says? For intervals of 0.4.
No, we did the first one first, and then we did D, and then we did D. We did 1, we did A, and we did D. Something else. Unless you pick.
Okay, and so for part A, are these going to be horizontal lines or something else? Sam, what do you think? Did you draw horizontal lines or something else?
No.
Okay, so what did you draw?
It's like the piecewise function.
Okay. And how do you specifically draw the piecewise function? Like what defines how you drew it?
So I did like from 0 to 0.4.
Uh-huh.
And like I like connected like those points with a straight line, so it's like the constant, like is it rate of change? No. Yeah. Rate of change. Or it's
Is
like
it?
constant. Yeah.
What's constant? Is the
The rate of change.
rate of change is
Yeah,
constant.
hold it constant for that interval.
And what about the volume of the sphere? Is it constant?
So the approximate, yeah. No, I don't know.
So in this approximating function, tell me about the volume. What's happening to the volume? Changing? Increasing. How much does it increase in each interval?
By a constant rate times the largest change in radius.
Okay. But the amount of change that you guys are drawing isn't determined by a calculation. How much does the volume change in each interval? It's not about a calculation or computation. How much does the volume change in each interval? Why did you draw it that way and not? Why did you not draw this? Or this? How much does it change in each interval? No. How much does it change in each interval?
The final volume minus the initial volume?
Was that? Right, yeah. So you're choosing the points at the end so that it changes the same amount as the actual sphere does in that interval, right? So the overall change in y, say for the second interval, change in volume, is the same as the actual change in volume. Do you see that? And so and you also said it's a constant rate. So that's what you're doing. You're creating a constant rate that achieves the same change in volume as the sphere actually changes in volume over that interval. And so what is that? What is the change in the, what is the constant rate that achieves the same change in y as the original function? That's how we define average rate of change. What did we say the average speed was in the Falling Marbles project? Average speed was constant speed to achieve the same amount of distance over that amount of time. So it's the same thing. You see, it's the same thing. So we're choosing a constant rate. You drew constant rate that achieves the same change in volume for the same change in radius, which is exactly analogous to average speed, which is the constant speed to achieve the same change in distance for the same change in time. Okay, and so then we wrote, so we skipped up to D, right? So let's do that again. So here we are, and so what in D we want to write for any given interval, say that second interval. It could be the second interval, the third interval, whatever interval it is. So we're in the current interval right here. How do you write that constant rate of change? How do you write that constant rate of change for this current interval for this value of x right here? So given that value of x, what formula gives you this constant rate of change? So remember that. Okay, so given that current value of x, we want a formula that will determine this current constant rate. So the question is, how do we write the rate of change of that segment there? That's the current segment being built, right? The current segment that's being generated. How do we write the rate of change of that? So the key to that is the coordinates of the points that you're going to use, right? So if you know the coordinates of the points, the endpoints of the current interval, based on that value of x, then you can write the rate of change. Okay, so this, what's the coordinates of this first point? Let's see. How about Morgan? What is the coordinates of this first point right here? Right. Okay. And so then we need the coordinates of this point. Where are the coordinates of this point? Sing. This point up here. Yeah. So this was, so if this is left x and f of left x, then what are the coordinates of this point? Uh-huh. Good. And so now if we've got the coordinates of those points, then we can write out, now we can write what the rate of change is. Ryan, what you got? Mm-hmm. So say it again. F of this one? Minus. Right? Change in y over change in x. So that's generic for every interval, right? That's the beauty of that left x function, is that it will give you the right rate no matter where x is, right? No matter where x is, it'll pinpoint the current interval and give you that rate of change. So this is a function that works in every interval. You don't need a different rule for every interval. That's the beauty of left x. Okay, questions on that? Okay, and so then we said, can you write this approximate accumulation function? Again, generically, you just focus on any one given interval. Say right here. And what are we trying to do? We're trying to writing that function means writing the y coordinate of that point, which is the y coordinate of the current value of x. So we're writing y equals what? That's not a fraction bar. That's just a fill in the blank. Okay? That's not a fraction. That's a fill in the blank. So if by writing the y coordinate of that point, you are in essence writing what that function is, right? You're writing what that function is. Again, this could be any interval, right? So this could be the 10th interval, it could be the 15th, it could be the 2nd, 7th, doesn't matter. It could be any interval. So this is going back to number, is this B? Okay. And this is that very important concept we've been working on. If we want to draw a line, So hint, we think of the y as, here's a hint. Think of the y as y final. Think of the y as y final, that's a hint. And this is a big topic that we've revisited many times. So I'm going to come around and see.
So that's your dy. That whole thing. So the y initial applicated whatever we do. Unless and about like the rule for exponents, or you just subtract. But we were trying to make it more conceptual. So we were trying to make the lesson more conceptual, and like I would just really be a question and I would just tell you the answer, and I'd give you questions again. And so we were trying to do that. And at the end, like the people at the end, people in the class had to like do a survey thing of what they thought of our lesson. Like six or seven different people said, don't be condescending to your students. Don't like just to our group. Like don't be condescending to your students. Don't be rude. Don't be no. It was me. Like at one point we talked about like something being imprecise and not how to calculate it, and like there was a huge like people were like, yeah, but we're saying that's what it means.
Okay. Megan, can you take me through it? All right, let's regroup. So, yes, how would you think about it to set it up? Yeah.
Okay, so I was thinking that y final equals y initial plus the change in y.
Okay.
So for my y initial, I said it was f of left x.
Y, she wants y initial to be f of left x. The y, and so that, what is that? That's the y coordinate at the start of the interval, right? Okay.
And then the change in y is equal to the rate times the change in x.
Right.
So that the rate was r of x.
So that thing we just found. That okay.
And then the change in x is x minus left x.
And this thing is the thing we just found, right? That average, the average rate of change for each interval, right? That's the Rx. Average rate of change that gives it for each interval. Okay, yeah, so y initial plus the change in y. Y initial is the y coordinate at the beginning. Rx times left x. So now I want you to do next is sketch Rx. So our whole, what is our goal here? Why do we make this approximate rate function? So that we can create a rate of change function. So it's like we've got amounts and we want rate of change. And so the way that we get started with that is with this approximate volume function that has constant rates. So can you sketch R of x over here? Sketch R of x over here. Okay. Did you get this? So is this what you got? Does it make sense? Right? Because we're drawing what? We're drawing the rate of change of our approximate accumulation function. And that's based on what? Constant rates in each interval. So those are going to be horizontal lines. So we don't want, so we won't take the time to get all the values. So just the general idea that you have constant rates that are increasing with each interval, right? Constant rates that get higher with each interval. Okay, and so we all know this principle that as you make h smaller, your approximate accumulation function will be closer to the actual accumulation, and then the approximate rate will be more accurate as well. So let's do that. So here's h of 0.27. Now it's too slow. There's h of, what did I say? 0.2755. Okay, even smaller. And so what happens, then these constant rates start to form a general rate function. And so we can kind of start to see that the actual rate function forming there. But that's still a whole bunch of itty bitty constant rates, right? So then we imagine for a super small h, we're going to have the exact rate function. So when you make h very, very, very small, you get this red curve. So again, here is showing the approximate rate function, which is made up of a bunch of constant rates for h equals 0.005, and then here's the actual rate function, the smooth continuous curve, which is like, just make h be a lot smaller than that, and you essentially get this graph. Okay, so any questions on that? Any questions? So this is good, and it reverses the process that we talked about before with sand unloading. But the left x is kind of prohibitive when it comes to working with that formula. So we want to kind of smooth this out, right? So this left x version is kind of like a chunky version, and so we want to smooth this out. So let's look at how we can do that. And this is the new stuff. And we have 5 minutes left. Okay. So here's what we did before, right? Here's what we did before. And so now imagine this instead. So I'll keep the old way, but then this blue interval, it slides along with x. So what? So the left side of the interval is always with the current value of x, as opposed to these left sides that we set ahead of time. So then it just slides along with it. Now h is still 0.4, it's just that the left side of the interval is always the current value of x. Not 0, 0.4, 0.8, 1.2. It's always the current value of x. Okay, so now we don't really get an approximate accumulation function, but we can still calculate the rate of change given this sliding, the smoothed out version. And this is actually much easier. Okay, this is actually much easier. So find the approximate rate of change for any current value of x. So for the current value of x, what's the approximate rate of change that is represented by the blue secant line, right? So what question is that? So let's do these questions. Will the secant line rates of change be constant rates that change abruptly or something else? Question A. What do we think? What is that something else? So he's saying now that the rate of change based on the blue secant line is going to be gradually changing rather than chunky. Okay, what's question B? Will the rate function using the blue secant line, will it be approximate or exact? So will the rate function that we get by using the blue secant line, they're saying still approximate. Still approximate. Everyone says still approximate. You're so smart, okay? So then, we want to write the rule. Skip C, we'll just go right to write the rule. Write the rule for now write the rule for what? The constant rate of change represented by that blue secant line for any value of x, and that's essentially you're writing the function for the approximate rate of change. Ben, did you get it? So tell me what it is. Ben's going to tell us. Here we go.
So it's just the same as before, but you don't have the left x. So if you're looking at, it's just y equals, then you have the f of x plus h minus f of x over h. That's what all times are, right?
What about that? Okay, and so will this, so you said this rate function is approximate or exact? All right, it's approximate. So in this case, is it too high approximate or too low approximate? Too high or too low approximate? So let me show it. No, I'm asking. Here's the rate function that you will get from calculating the rate of change of the blue secant line. Is that too high or too low, and why? Is that too high? You're saying, tell me it's not exact. Is it too high or too low, and why? Why? Okay. Chloe, do you know why it's too high? Okay, so here's the current value of x. I'm going to zoom in. So now you're looking at the local linearity of the curve is black, and then the secant line is blue. Is it too high, or is the approximate too high or too low? It's too high, right? The approximate is based on the rate of change of this blue line. The actual rate of change is represented by this the little part of the black curve. So here's the actual rate of change function. The blue one predicts too high because it's always steeper. The y is changing too much at the local point x than what x actually does. Does that look familiar?